Thank you. Okay, you can relax. No chemistry involved. Okay, so this will be completely different. That being said, we are going to talk about technology, IoT, Industry 4.0, AI. We're all hearing a lot about this these days, and particularly with regard to how it's going to revolutionize the way that we make our products. So it's real exciting. So if you ask all of the experts out there, pick any one, what parameters should I be controlling? You'll get a quick answer, all of them. That's easy to say, but it's a cop-out. It isn't practical. So let's get into that and talk about it. Now, we're all familiar with the Internet of Things, okay? The smart devices around our homes that allow us to control our lights, our thermostats, our garage door opener for that matter. IIoT is the Industrial Internet of Things. And it means getting information relative to your process into a shareable format so that it's easily accessible to all parts of your company simultaneously. And this is often extended to mean from anywhere or on any device. The goal, make it easier to analyze the data and control all of the aspects of our manufacturing process so we can be more responsive with the goal of managing change as it occurs. Problem is, it's an analog world. The things that we're trying to achieve with our coatings, things like color or gloss or orange peel, and also those parameters that end up affecting these outcomes, things like humidity and temperature, pressure, flow, and even viscosity. All of these are parameters that have to be digitized and moved into a database if we're going to analyze them. So what parameters are we talking about? Well, there's things like temperature of air, of paint, humidity of the air. There's flow of the air in the paint. There is pressure. There's viscosity. There's level, speed, voltage in the case of our electrostatics, velocity, again, of air and of the robot that's laying down our coatings. And then we've got the outcomes that we have to be attentive to. Our film build, our color, our gloss, orange peel. We've talked a little bit about those. Model. These are all measurable parameters. There's devices out there to measure them. But then there's visual components as well. Things like run and sag, blister, pop, etc. Now, there are vision systems that can do this. We'll talk about the complexity of those in a little bit. The problem with all of these is that sensors are expensive, especially in the paint shop. They have to be ruggedized. They have to be intrinsically safe. They've got to be cleanable. And oftentimes they have to be designed so that they can be cleaned in place. There's the cost of the sensors themselves. There's the installation of the sensors, the supporting network to gather the data, the processing involved after we've got the data, the energy that it takes to power the sensors. And then there's the data storage. And this is an exponential cost. It grows day after day after day. We'll talk a little more about that as we go through. The problem is, some of these things are ignored at the beginning of our project, and that makes for some pretty rude surprises on the back end. In a paint shop, again, because these sensors are intrinsically safe and very demanding, they can run anywhere from $2,500 a point to $35,000 a point. So they add up in a hurry. Let's take a quick example. Just a simple 10-color paint shop, standard plastics type thing. And we're going to talk about laying down paint. So we're going to ignore things like the warehouse and inventory and all of that kind of thing and jump right into the paint handling process. And that all starts here in the mix room. Now, when we look at that, Just for 10 colors, we're talking about a minimum of 51 sensors at a cost of $250,000. So it adds up in a hurry. And you might want to add things to that, like solvent tracking and energy consumption and tracking waste and things like that. From there, we have to get it to our process. So it moves into the circ system. Here, we've got several other parameters that we need to monitor, about 40 sensors worth, to a tune of about $200,000. Quick math, we're into this almost $500,000 and we haven't painted a part yet. That's a problem. So let's move into the areas where we're going to do that. Let's move into the prime booth. Here, we got 2 robots and everything is controlled after the color stack. So we've got fewer sensors involved. A mere 24 grand to equip this 2-station paint system. But we might also want to be looking at things like compressed air consumption and energy consumption. And then, of course, there's the robot controller. It makes tons and tons of data available to you. Which ones you decide to store are entirely up to you, but remember, you're going to pay for that storage. So that's important. When we move to the base coat booth, we now have 4 robots, 2 on each side. Almost twice the sensors, about twice the cost. And again, the same other options for monitoring in this booth. When we move to the clear coat booth, we're going to see the same thing. Another 4 robots, same cost, same sensors, same additional options, including all of those robot parameters. And again, twice as many as the prime booth. Now, I'm going to skip the oven because the oven comes with its own package of sensors and that kind of thing. Not that it isn't important, but we're talking about laying down paint today. So we're going to stick to our knitting. When we look at the QC shop, we've already talked about a lot of the things that we have to monitor. Just for this little 10-color paint shop, we're going to need a minimum of 15 different devices. That's going to rack up another 150 grand in cost. So I turn back to run and sag and blister and pop. Those are visual, manually inspected, manually entered. There are vision systems out there, as I've already mentioned, but talk about cost. It's going to swap out most everything that we've seen, and the amount of data that it will generate will create a financial hardship on the other end as well. So if we just do a quick summary, we're talking about a simple 10-color paint shop requires 150 sensors at about $750,000. Why would we do that? Well, it's the promise of AI, of course. And that's a great promise. It's things like the reduction of operating cost, removing bottlenecks so that we can increase our output and accelerate our revenue growth, and streamline our customer experiences and improve our compliance, sustainability, and our risk management capacity. We want to reduce our supply chain friction and eliminate every second of downtime and every ounce of waste. At the same time, we want to eliminate operator judgment and intervention with the goal of achieving a true lights out factory. That's a pretty powerful appeal, isn't it? That's why you would do it. But AI comes with some inherent problems, and you got to be aware of them. In the first place, we've already demonstrated the cost of the sensors, but there's additional investments required. There's large data centers that you have to have. And then there's a storage cost. I've talked about the data. You say, that's 7 terabytes per month or $7 per terabyte per month. That's not that big. But let's say today I generate 7 terabytes, or I generate a terabyte. That's $7. Tomorrow I generate an additional terabyte. Now it's 14. By the end of the week, I'm at nearly 50 terabytes or $50. And or by the end of the month, I'm at about basically 350. So when I start looking at that, that's $350 per month. So it's multiplying out very, very rapidly. So the cost adds up in a hurry. To process all this data takes a lot of expensive chips. Right now, NVIDIA's Blackwell series running anywhere between $30,000 and $40,000 a chip. That's a handful of cash right there for a pretty small chip, by the way. And we've all heard about the huge energy requirements. It's all over the news. If you haven't had your head in the sand, you've heard about the energy required to support data centers, okay? Now, right now, data centers use more electricity than a whole bunch of countries, okay? And it's swiftly gaining on the others. And the fact of the matter is, it's only going to get worse. McKinsey and Company noted that data center power consumption is going to continue to increase at a 10% compound annual growth rate, exceeding 35 gigawatts by 2030. It's going to be the lead energy consumer in the world by 2030. That's pretty fast. So that's frightening. The real problem is what I call a process data conundrum. And AI is not a thinking machine, it's a predictive tool. It looks at this huge database and it says, what's the next most likely word or sentence or phrase or event? But it's based on history projected forward. And that means that you need a large database. We often refer to these as large language models. Now, it just so happens that when we're dealing with language, the meanings and the implications and the structure are fairly well defined. And we've been using language and generating it in volume for centuries. We've been moving it to the internet for the last 3 decades. Processes, on the other hand, are a little bit different. They require large data sets. And the real issue there is that the data is often not readily available. And we'll look at some examples of that. In fact, Jennifer Heathcote from GEW UV at the RadTech Winter Meeting just at the end of January, a couple months ago, she was standing and she was talking and she said, hey, the problem is the process data sets simply don't exist. And I went, ping, we need to talk about that. And it's true. The problem is that the data is stored in disparate sources. You've got whiteboards. You see them on the shop floor all the time. You've got paper, you've got notebooks, you've got books and magazines. Even if it's electronically stored, it may be in a Word document or a Google Doc. It may be in Excel or a Google Sheet. It may be in a database like Access. And these may be accessible from a local computer that is not always available. And then there's portable data sources like memory sticks and SD cards and things like that. Not only are these not always available, they also pose a significant security risk. So this is a real problem. Oftentimes, the data resides on the machine. First in, first out, you're losing data as fast as you're collecting it. And oftentimes, you lose all of your data when the power is removed from the machine. If you're lucky, it may be attached to a factory information system where you can store that data. Regardless, all these different sources are going to have to be combined and placed on a central database where AI can access it, or it has nothing to use to project. So this is a huge cost right from the get-go. And no discussion of AI would be complete without talking about hallucinations. And if you haven't heard what a hallucination is when your AI system outputs something that's just gibberish. And we see it all the time, okay? And this is from Electronics 360 News Desk. Either it's not based on the training data, it's not decoded properly, doesn't follow any identifiable pattern. The outputs are nonsensical or inaccurate. Who here wants that associated with their manufacturing process, especially their painting operation? Yeah, I didn't think I'd get anything. Oh, I got one. So, how often does that really happen? Not often, right? Well, the Electronics 360 News Desk goes on to publish the hallucination rates of the top 15 AI models. Take a look at those. What this graph is telling you, this graphic, is that you're going to have to accept an error rate of 1.3 to 3% when you turn your painting process over to AI. Is that doable? I mean, what's causing this? Errors in encoding and decoding, high model complexity, that's a paint shop, and other factors like bad training or bad data. We've already talked a lot about the data. But while this is okay for a term paper or a blog post, can you really put your manufacturing output into a system that already has 1.5 to 3% error rate? If you're trying to manufacture 99+% first pass yield, I don't think you're going to get there. So why does this happen? Well, I'll give you a hint. We're 2/3 of the way through this presentation. And by now, you're probably asking yourself, who is Saint Clair Systems and what do they know about this stuff anyway? Well, we design and manufacture advanced point-of-use temperature and viscosity control systems for industrial fluid dispensing operations. Been doing it for about 35 years. And we do all different types of systems. Low viscosity fluids like water and solvent down around 1 centipoise, all the way up to high viscosity adhesives in excess of 1,000,000 centipoise. So who cares? And the answer is lots of folks across myriad industries, as you can see here. Okay. In fact, as I stand here right now, there's more than 3,500 of our systems shooting goop of every imaginable type on products of every shape and size, virtually everywhere in the world. In fact, some of you may recognize your companies here, and that means that you have our equipment in your plants. We have published countless articles and case studies on how different fluid parameters affect the outcomes of the process. Paints, coatings, sealers, adhesives, you name it. And while I grant this is a shameless advertisement for Saint Clair Systems, it's also the reason that we're qualified to stand here today and talk about this. I mentioned we focus on viscosity, and viscosity is a unique case. What makes it unique? It is the poster child for everything that's wrong with process data. Allow me to demonstrate. In the first place, it's generally a manual operation. I take a dip cup, I take a stopwatch. This is totally dependent on the motor coordination and how hungover our operator is. And might not get the same results 2 trials in a row, I'll bet not, just based on motor coordination and attention to detail. So it's a manual operation. And this means it's inherently inaccurate. Moreover, it takes time, so it's often taken infrequently. Maybe the first of the shift, maybe a couple times a day, maybe hourly if I really got good operators and lots of time. It's also being manual, generally recorded on paper. Now, it may be moved to a database, but this is where it starts. But it gets worse because there are as many different kinds of measurement tools and units of measure for viscosity as there are engineers to come up with a way that they want to do it. And This is not like converting from degrees Fahrenheit to degrees centigrade. There is no Rosetta Stone for all these different ways of measuring viscosity. So how do you coordinate that? By the way, I think there's 49 of them if you count, and that's not all of them. It's amazing to me as a guy who has to deal with this every day. So let's look at an example in production. This is in a paint shop. And what they've done is recorded their manual readings for temperature and viscosity. And what do we notice here right off the top? In the first place, it's not done on a consistent rhythm, on a consistent interval. So that's a real problem. I mean, on the weekend, there's nobody there, so it isn't done at all. So there it sits. Now, when I look at this data, can I correlate temperature with viscosity? Whether I'm somebody who does this every day and knows that there's a relationship, or whether I'm an AI model. Well, they're preparing to move forward into automated control. And so they installed our VTS, which is a viscosity temperature sensor. Original, huh? But what it does is it logs in real time, both temperature and viscosity. And it does it on the same base. And it even does it through the weekend. And with this, anyone can look at this, any individual, any AI system can look at this and create a direct correlation, the one that we all know to exist, between temperature and viscosity. As temperature increases, my viscosity falls, and vice versa. So this makes sense. And this is what you have to do. But then you have to correlate this to your defect data in order for it to make sense. And if you don't, how can you expect AI to go out and be able to predict what's going to happen based on what it sees in your system? So it's important. And so, to control or not to control? That is the question. And it doesn't depend on your process. Everybody starts at their paint shop. Don't. Start with your customer. Understand your market and your customer. Are they keying on film build or color or gloss or orange peel or scratches or adhesion, or the list goes on? What's important to them? And then once you understand what your customer is looking for, focus on those process parameters that affect those critical outcomes. And then you can decide what parameters should we monitor. And that's done by identifying those process parameters that directly affect our critical outcomes, and then identifying the cost-benefit relationship of each one so that we can classify them in order of importance to us and to our customers. Create a Pareto. And then install monitoring only on those parameters that you intend to control. Because why would you monitor parameters and store that data and pay to store that data if you have no intention of affecting it? And then, of course, what parameters should we control? And the key question, when? To do that, you have to identify your budget and your implementation capacity. If it's a greenfield shop, you may be able to do it all at once as you're building. But if you're going back and retrofitting, and most of us are, then you need to understand your budget and what resources you have to implement this capacity. And then you go back to your cost-benefit analysis and your order of importance to your outcomes, and you implement control on those parameters in that sequence. But you're not done, because as I mentioned, you still have to establish that cause-effect relationship so that you understand, and so your AI can understand what changes in parameters mean to your end user. Then and only then should you consider implementing AI to control your process. And with that, I thank you for being here. I thank you for your time and attention. And I will open the floor to questions unless everybody wants to make a mad dash to be the first in line for lunch.
Thank you very much, Mike. A wonderful presentation.
Thank you.
After seeing your talk today, I know why you're a repeat presenter here. A wonderful job.
Well, thank you.
There's I think last I looked, there's only a few questions in here, so I would encourage you guys to put your questions into the app, or I'll pass the phone around. The first question is, of all the viscosity measurement methods, which ones have the lowest percentage of hallucinations? Has AI helped you to make a recommendation of what would be the most reliable method?
AI has not. Most paint shops, many processes aren't really at the level of implementing AI yet. A lot of folks have started the process, but they're finding out as they get into it, it's not really there. You can often do a better job with simple Six Sigma statistical analysis and doing it that way. The trick for viscosity measurement in particular, to address the question directly, is all about picking a method of measurement that does not involve manual operations, okay? It needs to be something that can automatically and consistently, reproducibly measure the viscosity. It's gotta be mechanized. You can't do it off manual measurements. And the reason is they're too far apart. I can't tell if the measurement that I took this morning has anything to do with the orange peel I'm seeing right now. There's too much time in between. You can't make that inference. I can't do it, and AI can't do it.
Certainly, if that manual measurement necessarily doesn't get entered into maybe an hour or two later, where you sort of miss that window when it truly did occur.
Well, and if, you know, temperature changes just as surely as the sun comes up in the morning and goes down in the evening. By the way, on the day that doesn't happen, we're not going to care about the viscosity of our paint. However, that said, it may have been fine at 8 o'clock this morning, but as we approach noon, things may be all out of whack. How can that be? It's the change in our environment. So,
good answer to that.
Thank you.
Tough question. You did mention a little bit knowing the market, knowing your customers. How has collaboration been a sort of a key requirement for you in your business?
Oh, that's essential. Because everybody thinks it's like this, and it can't be. You've got to work with your customers, okay? Every process is a little bit different. And for instance, for us, where we place the devices in the process, how they're maintained, and how you keep them clean, keep them operating properly, it's critical. And so you have to work with your customers. They have to work with their customers. And so it's a long-term collaboration through multiple layers in the process itself.
Perfect. I think that's a great answer, and really a challenge to all of us to really work closely together. Are there any other questions in the room? You sort of ran out. Brian?
Really appreciate the presentation. When you said shooting goo, you really pulled at my heartstrings as a painter with lots of sealer in the paint shop. You know, one of the other challenges that I've seen, you know, in terms of viscosity is a lot of our materials are affected by shear.
Yes.
So from a sensor standpoint, what kind of recommendations you have for those processes that, you know, you've got a viscosity in the drum, a viscosity in the pipe, and maybe a different viscosity at the applicator. How do you monitor or control that?
Boy, that's an excellent question. And in fact, I do a whole presentation on thixotropy. And the issue is that it changes as you point out. You've got one thing in your drum, you've got another thing in your lines, you've got yet another one when you hit the atomizer or when you hit the nozzle in the case of streaming or extruding. And all you can do is pick a point as close to the point of application as is practical. Ideal is right next to the nozzle, but that's not always practical. And then you have to understand what the shear is at that point and what you expect to measure at that point. You talk about collaboration. This is where you get in with your customer and you say, if you're going to reproduce correct results time after time after time, you're going to measure temperature and viscosity at this point, and they have to be within this range. And then when they hit your applicator, they will behave as such. And that really is a collaboration between the material supplier, the equipment supplier, the end user, and their customer to make sure they get it right. I just came out of the Henkel presentation, and all of their samples are applied, and then they're skivved down on one end and brushed down on the other because they expect that. Really? How can that be possible? You spend millions of dollars on very high-tech robots and very high-tech control systems, and you got a person at the end of the line with a paintbrush brushing out seams. How good a job is he doing? Is his heart really in it? And why did you spend all that money in the first place? Let him put it down while he's standing there. So it does come back to all of those different things working together. But yes, you got to pick a point. You got to know what the characteristic is at that point. And you're right, when you start looking at thixotropic behavior, it gets really, really tricky. And it also ties back to the sensor that you choose, because some sensors have a higher shear rate than others. So you got to understand how your sensor is shearing the material to understand how it's all going to behave in your system. So that's a long-winded answer to a really quick question, but a really good one.